Hello, and welcome to the video lecture for topic 25, Organic Redox Reactions, Part 1. Now, unlike in Gen Chem, redox reactions in organic chemistry can sometimes be a little challenging to recognize. And so we're going to start off by looking at how we determine oxidation states in of atoms in organic molecules, and from there we're going to move on to look at some of the oxidation and reduction reactions that we need to be aware of here in Chem 201. So, like I said, let's just start off by seeing how is it that an organic chemist determines the oxidation state of an atom in an organic molecule. Well, we're going to take methanol as our first example. So we have a carbon, 1, 2, 3 hydrogens to an oxygen to another hydrogen. We need to have all of our lone pairs present. Now, to determine the oxidation state of any of these atoms, the first thing that we're going to do is we're going to break all of these bonds and assign the electrons to the more electronegative atom that's part of the bond pair. So, for example, looking at my carbon-hydrogen bond here, carbon is more electronegative. I'm going to assign both electrons to the carbon atom, and the hydrogen will take none. We can repeat this process for our other two hydrogens. Again, carbon's the more electronegative. It gets both electrons. And finally, for our third hydrogen, like such. We can do this also with our carbon-oxygen bond. Here now, oxygen is the more electronegative atom. So it's going to take both of the electrons from the carbon-oxygen bond. And finally, in the oxygen-hydrogen bond, oxygen is more electronegative. So it takes both of the electrons from that bond as well. The next thing we do is we're going to use a little bit of math. And I know, I promise no math, but this is really easy, trust me. Right? And what we're going to say is that the normal number of valence electrons minus the current number of valence electrons, that's going to equal the oxidation number for that particular atom. So if we take a look at our hydrogen atom here, hydrogen normally has 1 valence electron. In this situation, it has 0 valence electrons. 1 minus 0, positive 1. So my hydrogen atoms all have an oxidation state of +1. Now remember, this is their oxidation number or oxidation state. It's not the formal charge on that atom. It's just what its oxidation state is. If we look at our carbon atom, carbon usually has 4 valence electrons. Right? So normally carbon VE normal is going to be 4. Our valence electron currently is 6. 4 minus 6. Our oxidation state here for carbon is going to be -2. And we can repeat this process for oxygen. Oxygen normally has 6 valence electrons. Currently it has 8 valence electrons, which also gives it an oxidation state of -2. Now, going back to what I said just a moment ago, these are oxidation states and not formal charges. And we can see that because if we add up all of our formal charges together, 1, 2, 3, 4, minus 2 is 2, minus 2 is 0. Overall, we have a neutral molecule, right? Nothing's got a formal charge in methanol, but now we're able to determine the oxidation state of each atom that's present. So we need to look at one more situation, right, or two more situations, double bonds, and what happens if we're breaking a bond between two of the same atom. And a really great example for that is going to be acetic acid. So here I'm going to draw out the framework of acetic acid without any bonds. Excuse me, that oxygen shouldn't be there. So you can see here I've got that basic framework for acetic acid. I just haven't drawn any of the bonds in. So normally there'd be a carbon-hydrogen single bond here, and carbon would take both of those electrons. Same for these other two hydrogens. However, now, normally here I'd have a carbon-carbon single bond. Both of those carbon atoms have equal electronegativity, so we divide the electrons equally, and each carbon atom gets one of those electrons. We can move on to our oxygens, right? Here we've got the lone pairs for those oxygens. Normally here, I'd have a carbon-oxygen double bond. Remember the structure of acetic acid? Looks like this. So right now, I'm just taking a look at that carbon-oxygen double bond, and I treat each of the bonds individually. So for the pi bond, oxygen's more electronegative. It's going to take both of the electrons. And for the sigma bond as well, oxygen being more electronegative, it'll take both electrons there. For now, looking at this next carbon-oxygen single bond I have down here, again, oxygen being more electronegative, it takes both electrons. And finally, for this oxygen-hydrogen single bond, oxygen being more electronegative, it's going to take both electrons. So now we can see that in acetic acid versus in methanol, our carbons have different number of electrons. Hydrogen's the same situation as we saw in methanol, so those are all going to be +1. Our oxygens are the same situation. Those are going to be both -2. However, now, this carbon, the carbon of the methyl group, it currently has 7 electrons. It normally has 4 electrons. That means its oxidation state is going to be a -3. Our carbon atom that was part of our carbonyl group, it normally has 4. It currently has 1. Its oxidation state is going to be +3. And again, if we go through and we add up all of our charges, we'll see we have 1, 2, 3, 4, 7. So we add a +7 if we count all the atoms that have positive oxidation states. And we have -2, that makes -4. 3 more, that makes -7. And our overall oxidation state for the entire molecule is 0. We have no charges, so overall we are 0 for this molecule. So now we can have a method by which we can calculate formal charges on atoms in an organic molecule. What this then allows us to do is it allows us to track changes in those oxidation states when a molecule goes through a reaction. So for example, ethanol, when it is consumed by humans, is oxidized, and our symbol in organic chemistry for a molecule being oxidized, right, goes in these brackets. But when this is consumed by humans, an enzyme called alcohol dehydrogenase oxidizes this ethanol into an aldehyde. And we can track the changes in oxidation states in the different atoms if we using this process we've seen. And if we go through, we'll see that the carbon atom here starts with an oxidation state of -3. This carbon atom starts with an oxidation state of -1. And if we look now in our final product, right, our oxygen here is going to have an oxidation state of -2. And if we look in our final product and we do these same types of calculations, we'll see that that methyl carbon stays at a -3. However, this carbonyl carbon here now has an oxidation state of +1. And the oxygen atom stayed at an oxidation state of -2. So formally what has occurred based on this system that we can use is that this oxygen atom, which was an alcohol carbon, this carbon atom, which was an alcohol carbon before and is now a carbonyl carbon, has lost 2 electrons, right? We have decreased the number of electrons that we can say are owned by that carbon atom. And decreasing the number of electrons, losing electrons, when an atom loses electrons, it has undergone oxidation. Some other species has gained those electrons. That species has been reduced. However, if we go through and count everything, these are both going to be neutral molecules, right? And so going back to this concept of losing and gaining electrons, I'm sure in your secondary school chemistry classes or in Gen Chem, here you probably learned one of these two mnemonics. You either learned Leo goes Gur, and that stands for losing electrons is oxidation, gaining electrons is reduction, or you may have learned oil rig, oxidation is losing electrons, reduction is gaining electrons. Two mnemonics, just depends on who you learned it from, but they both tell us the same thing. Whenever an atom loses electrons, it has undergone oxidation. Whenever an atom gains electrons, it has undergone reduction. And so now I want to look at one last example, and then from there we're going to go ahead and start looking at, a couple more examples, and from there we're going to go ahead and start looking at some redox reactions, some chemical reactions that we can look at. So I'm going to clear off the board. We'll be right back. So the last example we just saw, we saw an alcohol undergoing oxidation, right? That's one type of process that we're going to see. The other type of process that we can see is an organic molecule undergoing what's known as a reduction. Right? And so I can take this alkene. Our generic symbol for reduction is a capital H in brackets for organic chemistry, and I can convert it to this alkane. By adding a molecule of hydrogen across that double bond. And if I go through and I do my calculations, right, for these carbon atoms, we're going to see that both of the carbon atoms in our alkene have an oxidation number of -2, whereas both of our carbon atoms in our alkane have an oxidation number of -3. Okay, and so that's a reduction. They have both gained electrons. So we've now seen how we can gain electrons, we can lose electrons. I want to show you one more example, right? Or, excuse me. What you've noticed is that in our previous example for oxidation, where we had this alcohol being oxidized to an aldehyde, we can notice some trends in organic molecules in that under oxidation we increase the number of carbon-oxygen bonds and simultaneously decrease the number of carbon-hydrogen bonds. You can see here we lost a hydrogen and replaced that with a carbon-oxygen bond. That is one of our signals that a redox process has happened in an organic molecule. Similarly here, we have increased up here the number of carbon-hydrogen bonds, right? And so that's a good signal. Increasing the number of carbon-hydrogen bonds, that's a good signal that we've gone through some sort of a reduction process. I want to show you a reaction we've seen before and highlight why this is not a redox. So we have seen where we can take an alkene, and if we treat that with sulfuric acid and water, we convert it to the alcohol. Now, here I have increased the number of carbon-oxygen bonds by 1. We would want to think that this is an oxidation. But I've also increased the number of carbon-hydrogen bonds by 1. And so overall, this doesn't really result in an oxidation or a reduction, because these two processes, increasing the number of CO bonds and increasing the number of CH bonds, is overall redox neutral. This is not actually a redox process, and there is an example in the POGIL worksheet that goes a good way to really highlighting it. Because one carbon atom is going to lose an electron, the other carbon atom is gaining the same number of electrons, so this is overall redox neutral for the molecule. We're not going to say that this is a redox process of any kind. Whereas increasing carbon-hydrogen bonds alone, that's reduction. Increasing carbon-oxygen bonds, either alone or simultaneously decreasing carbon-hydrogen bonds, that's going to be an oxidation. So make sure that you're careful in recognizing what is a redox process and isn't a redox process. You can use our organic chemistry shorthand, counting carbon-oxygen, carbon-hydrogen bond changes. But if you're at all confused, use the process shown at the beginning of the video lecture of splitting the bonds, assigning electrons to the more electronegative atom, and determining the true oxidation state. Okay, so from here now I'd like to go ahead and move into the reactions that we need to know for topic 25. So I'm going to clear off the board. We're going to start looking through those. Okay, so the first reaction we're going to look at is called catalytic hydrogenation. You'll often hear me just calling this a hydrog reaction. That's a bad habit left over from my grad school days, but it is actually known as a catalytic hydrogenation. And so what we mean by this is that we can take an alkene and this can be a cis or trans alkene. It can be monosubstituted, disubstituted, trisubstituted, tetrasubstituted. Really doesn't make a difference what the stereochemistry or the degree of substitution on your alkene is. They all work fairly well. And we can treat this with hydrogen gas in the presence of either a palladium catalyst, which is usually palladium on carbon, or platinum oxide, PTO2, and that completely erases that pi bond and gives us an alkane. Now, catalytic hydrogenation is a syn addition. So if I had a alkene with defined stereochemistry, under these same conditions I have here, those two hydrogen atoms are going to add to the same face of my alkene. So here I'm adding them to the back face of the alkene. And I'm going to form this compound plus its enantiomer, right? And so catalytic hydrogenation, this is a syn addition. Now, we can also do this with alkynes. However, it is not possible to stop the hydrogenation of an alkyne at the alkene. Under these conditions, palladium on carbon with H2 or platinum oxide with H2, this alkyne goes to form the alkane. And so we can't stop at the alkene. This is usually under a good deal of, there's a good amount, plenty of hydrogen gas around. So the alkyne gets converted to the alkene, and then the alkene is immediately converted to the alkane. So there's no stopping an alkyne in a catalytic hydrogenation reaction. Two things that we should be aware of. There are two types of pi bonds that don't react with catalytic hydrogenation. Those are the double bonds in an aromatic ring, such as benzene. Right? So here now, H2, palladium on carbon, there's going to be no reaction. in the benzene. However, if I have a double bond off of that benzene, it will react. So for here, example, styrene under these same conditions, the alkene off of the ring gets reduced, but the aromatic ring stays intact. The other pi bond that does not react by a catalytic hydrogenation is going to be a carbonyl bond. So if I take this ketone, which has a carbon-carbon double bond coming off of it, I treat this with H2. This time I'm just arbitrarily choosing to use platinum oxide. You could use palladium on carbon instead. Doesn't make a difference. Only the carbon-carbon double bond is reduced. The carbon-oxygen pi bond stays the same, right? So only the alkene gets reduced. The carbonyl doesn't get touched. Okay, so we have here with our alkyne a situation that we'd like to be able to deal with. With palladium on carbon or platinum oxide, I can't stop my alkyne from going all the way to the alkane. And so I'm looking for, as a chemist, I'd like to have a tool in my toolbox, a reaction where I can take this alkyne and stop at an alkene, either cis or trans. And so we're going to take a look at that next and see how that works. Quick note for you, all the reactions you see here, all of these catalytic hydrogenations, there is no mechanism that you need to know. There is a mechanism, but we're not going to worry about what that mechanism is for Chem 201. So I'm going to clear off the board, and we're going to take a look at how can I convert an alkyne into a cis alkene. Okay, so as promised, how can we convert this alkyne into a cis alkene? Well, there was a famous chemist named Lindlar who developed a modified form of a palladium catalyst that allows us to do this. So the modified form is palladium 0 mixed with barium sulfate, mixed with barium sulfate mixed with an organic molecule called quinoline, which has a benzene ring and a pyridine ring fused together that allows us to do this. And we also still need a source of H2, so hydrogen gas. So Lindlar's catalyst, right, palladium with barium sulfate and quinoline, right, there have been some advancements in this area, but this is the recipe I'd like you to know, allows us to take an alkyne to a cis alkene. Again, there's a complex mechanism for this that I'm not going to have you worry about this semester. Okay, so we've seen a few different catalytic hydrogenations that involve carbon-carbon pi bonds, right? Now we're going to take a look at some catalytic hydrogenations that involve nitrogen-based functional groups. So here there are three that we need to be aware of. So the nitro functional group can be reduced to an amine using hydrogen gas and our same conditions we saw in the last set of reactions, palladium on carbon or platinum oxide. And the nitro group then gets converted to a primary amine. Similarly, we can take an azide functional group and again, treating this with hydrogen gas, hydrogen H2, and palladium on carbon, is going to give us a primary amine. And then finally, taking a nitrile or cyanofunctional group, carbon triple bonded to nitrogen, also produces a primary amine, but this carbon atom picks up 2 hydrogens as well. And so we can get a new alkane type carbon, a new sp3 carbon is generated here, right? That sp hybridized carbon becomes an sp3 hybridized carbon, and right, that's why I'm drawing this carbon out explicitly. Our nitro and azide functional groups don't give us this new sp3 hybridized carbon, but our nitrile takes an sp hybridized carbon and sp3 hybridized nitrogen and converts both of those into an sp on the carbon and the nitrogen in cyano, and then sp3 and sp3 in the amine. Okay, so those are the catalytic hydrogenations, and that covers all of our hydrogenation reactions for topic 25. As I said, all of the reactions I've presented so far, there is no mechanism that you need to know. You need to be able to accurately predict products, provide reagents, or predict starting materials on fill-in-the-blank type problems. Okay, so next we're going to move on to take a look at some reactions that are formally oxidation reactions that we need to be aware of. And that's going to be the second half of the content for topic 25. So I'm going to clear off the board, and we'll be right back to see what those are. So the last set of reactions we saw, catalytic hydrogenation, we were always increasing the number of carbon-hydrogen bonds, and at the very end there we saw how to increase the number of nitrogen-hydrogen bonds, right? So these are formally reduction reactions, right? Everything we've seen before is a reduction reaction. And it all centered around H2 as a molecule and some sort of catalyst. So the first reaction we're going to see on the oxidation side of things for this topic involves molecular oxygen. And so oxygen, right, molecular oxygen has 2 oxygen atoms attached to each other, and in its ground state, right, in its preferred lowest energy state, the O2 molecule is actually a diradical, and this is known as triplet O2, which the shorthand for it as an organic chemist looks like that. That little 3 up above before the O indicates to us that this is a triplet. What the exact meaning of a triplet is, not super important for Chem 201, right? However, if you're interested in understanding what a triplet truly is, please come talk to me during office hours. Be happy to explain it to you. However, if we take O2 and we treat it with a molecule known as a sensitizer, and what a sensitizer is and how it operates is explained in your POGIL worksheet, so I'm going to leave that for you to find there. But if we treat it with a sensitizer and a photon of light, we can take it from its ground triplet state to its excited state, which is probably what you've seen molecular oxygen, or how you've seen molecular oxygen represented before. And so we take it to, this is the excited state, which is a singlet oxygen. And the shorthand for that is a little 1 in place of the 3 from the triplet. And singlet oxygen is actually a pretty reactive species. And we can do lots of fun, neat chemistry with singlet oxygen. And the chemistry that I want you to know from this is singlet oxygen reacting as a dienophile in a Diels-Alder reaction. So if I take a diene and my singlet oxygen, these 2 molecules can undergo a Diels-Alder reaction just like we've seen before in a previous video lecture, to give us this type of a peroxide molecule, right? This is known as an endoperoxide, but these singlet oxygen can go through a Diels-Alder reaction to give us these type of peroxide type molecules, which can then be further broken down to make lots of interesting compounds. So this is formally an oxidation, and the way we know this is an oxidation is if we look at the oxidation number for that alkene carbon, it starts off as a -2. So does this alkene carbon, starts off as a -2. And each of these oxygen atoms in singlet oxygen starts off at an oxidation state of 0. It's okay if you don't believe me. I recommend that you go through, split up the bonds, divide the electrons appropriately, and calculate the oxidation state for those atoms. However, if we look at the product of this Diels-Alder reaction, these two carbon atoms now have an oxidation state of -1. That means each of these carbons have lost an electron. They have undergone an oxidation. They have been oxidized. They've each lost an electron. And if we look at our oxygen atoms, they've gone from an oxidation state of 0 to an oxidation state of -1. They have both gained an electron. So the oxygen atoms gaining an electron is reduction. The oxygens have been reduced. The carbon atoms lost electrons. Losing electrons is oxidation. These carbon atoms have been oxidized. So this is one type of a redox reaction, right, where we're adding oxygen onto a dienophile in a Diels-Alder reaction. Similarly, we can do the same thing with dead. It's not just for Mitsunobu reactions. So if we take a look at dead, it can undergo the same type of a Diels-Alder process with a diene to give this type of molecule where we have added both of those nitrogens to our dienophile. Right? And it undergoes, right, dead will behave, the two nitrogens of dead will behave in the same way as singlet oxygen. Here, though, we don't need any sort of a sensitizer. This reaction proceeds relatively smoothly. Okay, so those are the first sets of oxidation reactions. Again, mechanism for this is just Diels-Alder arrow pushing, 3 arrows and the reaction's done. But we have a much more powerful reaction that we can use for oxidations, and it's a much more useful oxidation reaction known as ozonolysis. So I'm going to clear off the board, and we're going to come back and take a look at how does ozonolysis work, and we're going to take a look at the arrow pushing for that reaction as well. So the ozonolysis reaction is a method by which we can break carbon-carbon double bonds, and not just the pi bond, but the sigma bond as well, to create 2 new molecules. And so the compound ozone exists as a resonance hybrid between these 2 forms. And it can add in a concerted fashion across a carbon-carbon double bond like such, to give us a cyclic intermediate. I'm just going to rotate this when I draw it here. And let's go ahead and put some actual R's on this. Call this R1, R2, R3, and R4. So here's now, I broke my carbon-carbon pi bond. I still have my carbon-carbon sigma bond. And here's R3 and R4. And now my oxygen atoms, right, are making a 5-membered ring with my 2 alkene carbons. And we're doing arrow pushing, so we're going to remember to keep all of our electrons there. This intermediate is known as a molozonide, and it is extremely unstable. It wants to fall apart. There's a reason why all these oxygen-oxygen bonds don't like being oxygen-oxygen bonds, right? We have lone pair repulsion issues that are happening there, right? And so this wants to fall apart. And so this ring breaks apart like such. First, this oxygen-oxygen bond, single bond breaks to put the lone pair of electrons on that central oxygen. A lone pair of electrons from this lower oxygen here makes a carbon-oxygen double bond. The carbon-carbon sigma bond is going to break to make a new carbon-oxygen double bond. And we're going to get these 2 intermediates. So we have R1 connected to a carbon. Here's R2. That's double bonded to this oxygen. And then we have R3, right? Excuse me. We now have R3 and R4 connected to this other carbon atom, which has a double bond to an oxygen, and that oxygen is single bonded to another oxygen. Here are all of our electrons and formal charges. Again, these are 2 pretty reactive species. This negatively charged oxygen will attack this carbon atom. The electrons in the pi bond of the carbon we're just going into here, that's going to go ahead and form a bond to this carbon atom. Here we go. Let's make our arrow pushing lines a little darker. Right? And then finally, this carbon-oxygen pi bond is going to break, put the electrons onto the oxygen atom, and we will generate a new intermediate. I'm going to work my way up, give myself a little bit more space. That looks like this. And this intermediate is known as an ozonide, right? And now we can subject this ozonide to what's known as an oxidative workup or a reductive workup. Now, in an oxidative workup, right, there's a complex mechanism. I'm going to show you the reagents here in just a second. But the oxidative workup has a complex mechanism that I'm not going to show for Chem 201, that we're not going to get into. But the reductive workup is relatively straightforward. And so I want you to know the arrow pushing for our reductive workup. Our reductive workup begins with dimethyl, right, with dimethyl sulfide, right? And so the first thing that happens is this sulfur forms a bond to this oxygen atom, right? Those electrons from sulfur attack the oxygen atom. That oxygen-oxygen double bond breaks, single bond breaks to form a carbon-oxygen double bond. From there, this carbon-oxygen single bond breaks to form a different carbon-oxygen double bond, right? This is going to produce 2 products if we track our arrows. One, where we have the carbon that had R3, R4, so here we have C, there's our R3, there's our R4, that's going to have a carbon, excuse me, these electrons don't form a double bond yet. I got a little ahead of myself. These electrons actually just go right onto that oxygen atom. So now we have an oxygen with a negative charge, and then a carbon to an oxygen with that sulfur attached to it. Sulfur has a positive charge here. And then we have our other carbon atom that had R1 and R2 on it. We just have a carbon-oxygen double bond, right? So this portion down here just forms a new carbonyl compound, right? Whereas everything up here forms this big funky intermediate. And so the last step in our arrow pushing mechanism, right? Lone pair of electrons from this oxygen push down to form our carbon-oxygen double bond. This carbon-oxygen single bond comes around to form an oxygen-sulfur double bond. And so our other product here, we're going to have R3 and R4 in a new carbonyl compound. So this is the arrow pushing. Right here, I'm just going to put a mark that this is reductive workup. As opposed to an oxidative workup. Right? This is arrow pushing that you're going to be expected to know. You're going to be expected under any set of circumstances to be able to go from ozone and an alkene to the molozonide, rearrangement to form the ozonide, and you may be asked to produce arrow pushing for a reductive workup with dimethyl sulfide, right, where we can collapse this ozonide into two components, a carbonyl compound, a charged intermediate, and then show how this charged intermediate can then go to form our carbonyl compound and our other product, DMSO. Okay? So, arrow pushing you're expected to know. What I'm going to do is I'm going to clear this off, and I'm going to come right back and show you just the general conditions, right? How to compare reductive workup and oxidative workup of ozonolysis and be able to determine the products. Okay, so our general reactions for ozonolysis. Here now, I'm going to differentiate my two carbons a little bit differently than I did before, in that one of my two carbons, I'm going to have some sort of alkyl groups coming off of it, whereas on the other carbon, I'm only going to have one alkyl group and a hydrogen, and that's going to allow us to see what the differences in a reductive workup versus an oxidative workup are going to produce. In a reductive workup, right, so first I'm going to treat with ozone, and then second I'm going to treat with dimethyl sulfide, so SCH3 2. That's going to cleave this carbon-carbon double bond to give me a ketone on one side, two alkyl groups off my carbonyl, and an aldehyde on my other side. However, we have a different set of reagents we can use in step 2. So this is a reductive workup. If I start with this same alkene, this time now I'm going to treat it first with ozone, and then I'm going to follow that up. Instead of using dimethyl sulfide, I'm going to follow that up with hydrogen peroxide. What I'm going to find is that I'm going to get that same ketone out, but instead of getting an aldehyde from the other half of my alkene, this time I would get a carboxylic acid. right? So that hydrogen peroxide actually does a second oxidation to make, instead of making an aldehyde, makes a carboxylic acid. And this is known as the oxidative workup. Okay, so now we've seen ozonolysis, we've seen arrow pushing. For a full ozonolysis with reductive workup, you do not need to know arrow pushing for the oxidative workup, but you still need to know arrow pushing for reagent part 1, O3. Not going to worry about how the H2O2 takes it to the carboxylic acid this semester. Okay, so that just leaves us one more reaction to look at for topic 25, and we'll wrap it up after that. So I'm going to clear off the board, and we'll come take a look at osmium tetroxide. Okay, so the last reaction we're going to look at for topic 25, right, organic redox part 1, is going to be the reaction between an alkene and a reagent known as osmium tetroxide. So for this example, I'm going to start off with a cyclohexene. Osmium tetroxide, aside from being incredibly carcinogenic, is an excellent reagent for converting alkenes into diols, into 1,2 diols. And so the first step of our mechanism looks very similar to a Diels-Alder type cycloaddition. If we calculate our oxidation state of osmium here, osmium is going to start out at an oxidation state of, so this is osmium 8 is its oxidation state. We're going to track that once we get into our next step. And so what we see, the product of our arrows here, that is going to result in a syn addition. It's going to add, because this is concerted, the osmium, and we're going to form that, we're going to form this 5-membered ring. This osmium is going to come from a single face. And so we're going to do a syn addition of these 2 oxygens across the double bond. You can use wedges, or hashes. I'm just arbitrarily picking wedges, right? Whatever we pick, we need to track stereochemistry. But what we see in this first intermediate that we form is that osmium has changed from an osmium 8 to osmium 6. Right? Its oxidation state has decreased by 2. It has gained 2 electrons. The osmium has been formally reduced. If we do our calculations, right, oxidation state calculations that we've seen for these 2 carbon atoms, we'll see that both of those carbon atoms have been oxidized. So our first step is we form this cyclic intermediate after a syn addition of those 2 oxygens. We're going to then treat this with, right, part of our reaction mixture is going to be some hydroxide is in there. That hydroxide is going to come along, add into the osmium to break one of our osmium oxygen bonds. That gives us an O- off of that carbon. Right? Because this is attacking at the osmium, the stereochemistry at this carbon doesn't change. We still have this oxygen atom. It's now attached, it's still attached to our osmium. And this electron pushing reaction that we did here now puts an OH group on that osmium. It's still going to be osmium 6. Okay? We use excess hydroxide. So one more of those is going to come along and repeat this process we just did. And that's going to give us this diol that needs to get protonated, and our osmium byproduct, which is still at an oxidation state of 6. So this is the basic arrow pushing I need you to know. From here, you can just write H3O plus over an arrow. I'm fairly confident that at this stage, everyone in the class knows how to transfer a proton from H3O plus or from some sort of acid to an O minus. I'm not going to nitpick there if I ask you to do this arrow pushing. You can just go ahead and protonate. And we get our syn 1,2-diol, our cis 1,2-diol, lots of ways to describe it. And this is overall formally an oxidation reaction. Okay, so I've only shown you 2 of the reagents that actually go into this reaction. What you need to know is that really, it's not just OSO4 and hydroxide. We need to have osmium tetroxide, OSO4. So the reagent mixture we're going to use is OSO4. In addition to that, we need to have terbutanol. That's going to be our solvent for the reaction. Because osmium is, 1, extremely carcinogenic, we don't want to be using a lot of it in a reaction ever, and 2, ridiculously expensive because it's a pretty rare element. Like, there's not a whole lot of osmium floating around on our planet. We add in a reagent that can reoxidize our osmium-6 back to osmium-8. That's going to be done by tert-butyl peroxide. And finally, our hydroxide source is going to be NaOH. So this here in the box-ish thing, right, that is our full complement of reagents that allow this reaction to proceed. If this were a fill-in-the-blank style problem, you would need to include all 4 of those if you were asked to produce the reaction conditions: osmium tetroxide, tert-butanol, tert-butyl peroxide, and sodium hydroxide. We need all 4 of those reagents that allow this reaction to proceed. All right, and that wraps it up for topic 25, part 1 of oxidations and reductions. I'd highly recommend that if you didn't do so while watching this video lecture, make a list of the reactions we've seen, because if you go back and check, we've seen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different reactions just in this one video lecture, right? Most of those towards the beginning, we didn't have any arrow pushing we needed to worry about. A little bit of Diels-Alder arrow pushing for singlet oxygen and dead reacting with the dienophile. We had some arrow pushing on ozonolysis and a reductive workup. And finally, some arrow pushing here on our osmium tetroxide oxidation to a cis diol. All right, so that's what I've got for you for topic 25. Thank you for watching. And as always, if you have any questions, please feel free to bring them up in lecture, conference, office hours, or make appointment to see me one-on-one. Thank you very much.